Hello everyone, my name is Robert and this is Lab3Circuits. So the purpose of this lab was to use the principles of energy and current conservation to predict the behavior of series and parallel circuits of both resistors and RC currents. For this lab we used the PHYS circuit simulation for results after constructing some series, either RC or resistor in series. We found that the meters that they gave us are represented as ideal meters with tiny internal resistance, so they conserve all the energy in the circuit. For a 30 ohm resistor and a 200 millifarad capacitor, it had a time constant of around 6. So the fundamental principles used for this lab revolved around Ohm's law, as well as Kirchhoff's rules, mainly the loop rule, which we have the round trip is going to equal to 0 for each of the different loops, as well as how the resistors stack in a series versus parallel, and using Ohm's law to find out the total voltage and resistance of different parts versus using the meters. So going in order of the different parts of the lab, I first started with the diagram that they gave us with the 47 and 100 ohm resistor, and using the Kirchhoff's loop rule, I first started with delta V total should be equal to delta V1 plus V2 plus V3 should all equal 0. It turns out that EMF minus I1R1 minus I1R2 should equal 0 in that one loop. Since they are in series, it should have the same current. So on doing that equation, I found that the current should be around 0.0204 amps. Plugging that into the PHYS simulation, I found that it was a 0.02 amp current through both sides. If I flipped it, the ammeter, it still reported the exact same number. For testing the meters themselves, I found that the voltmeter connection had no impact on the output of the circuit since it broke the circuit anyway, which is measuring 3 volts across, so 3 volts from the battery means that there's no loss across the whole circuit. The ammeter itself as well reported no loss, so it had no internal resistance, making it an ideal meter. Going across the different portions of the circuit to find the voltage difference across each component, we found that the battery is indeed 3 volts. Across the 47 ohm resistor, it's 0.96 volts. Across the 100 ohm resistor, it's 2.04. That added up back up to the 3 total volts, so there's still a round trip of 0, upholding Kirchhoff's loop rule. Using that same diagram, I went ahead and filled in the rest of the plot. For the battery, since it's positive potential, it goes up to 3 volts. And then coming down for each resistor, drops down approximately 0.96 or around 1, and then the other 2 volts come from the other large resistor, and then the ammeter itself provided no resistance as it was ideal. When I placed the ammeter in parallel to a resistor, particularly the 100 ohm resistor, that ammeter formed a new path since it has less resistance, so no more current was really coming through the 100 ohm resistor, instead all passing through the ammeter, which, since it's in parallel, dropped the current down to 0.06 amps, so about half. Moving on to the RC circuit, once the circuit was connected between the 200 millifarad capacitor and a 10 ohm bulb, we can see that the current drops as the capacitor plates are charged until it matches the original potential voltage source, so the current stopped flowing once the capacitor got to around 3 volts as well. Doing the same circuit with the 20 ohm light bulb, we found that since the 20 ohm light bulb provides more resistance, it takes more time for it to charge as well as discharge, about twice as much as long as the 10 ohm light bulb. Using the equations that define the charging of a capacitor as well as the discharging of a capacitor as functions as time, we're going to go ahead and graph the discharge of the capacitor from its full charge. So go ahead and charge it up to its full 9 volts given the 9 volt potential source. And once we did that, using the stopwatch for every couple of seconds to measure out what the voltage readout was across the capacitor, we found that the slope of ln of the given voltage over the original voltage versus time was around -0.01668. Given that the slope is -1 over RC, the time constant for this graph is 6. So to wrap up, the capacitor charge and discharge behaves on a logarithmic scale as a function of time. To answer the what ifs, if an actual ammeter was used, then there would be some small internal resistance, as is not ideal, and that would cause a small potential drop across the ammeter itself when plugged into a circuit. Representing this in FET, if the capacitor is directly connected to the source charge, it will charge nearly instantaneously and probably produce a lot of heat and might explode. Fun.